Hi, I'm Ben-Yaakov. This presentation is entitled I2t, What, Why, and When, the Electric Fuse Case. Let me say a few words about the background. Now, overcurrent protection is used to protect circuits from damage. The protection will cut off the current when the set point is reached. This is not, however, an optimal approach, since the circuit can usually operate safely if the current set point is exceeded for some given time. That is, although you cannot run the system with the overcurrent, but for a short time you can certainly operate it. And this is because the limiting factor in many times is temperature and not current. That is, for example, if you have a transistor, the limiting factor is the junction temperature and not necessarily the current. Let me turn now to electrical fuse. Now, a popular belief is that the fuse will blow when the specified current is reached. In reality, it takes time for a fuse to melt. It does not happen at a specific current, but rather when the melting point of the wire is reached. So the magnitude, duration, and current shape will determine when the fuse breaks the current. Now, I2t, or I squared times time, is a measure of power flow, not just the current itself. It determines fuse behavior and can be used to protect electronic circuits in a clever way. This presentation is an introduction to the subject of I2t by explaining the operation of an electric fuse. Now, in a pioneering paper entitled The Magic of I2t, Kaufman actually pointed out to the many benefits and importance of this factor. He shows here, this is from the paper published 1966, quite a while ago, and here shows an electric shock to a person, and it turns out that the boundary between safe and unsafe areas is indeed I2t. That is, if you look at the current at time allowed, it turns out that this boundary is exactly 0.03 amps second, which is, by the way, joule per ohm, so that what is really important is the energy rather than the magnitude of the current. Another example is a fuse. You have a wire, and then this wire melts at a given point, at a given current. Now, this melting is not a function of the current itself, but rather on the heating of the wire, which is a function of I2t. So these are just examples of the many aspects of I2t which are really important in many processes. I'm turning now to the electric fuse. Now, the most important aspect of the operation is actually the thermal aspect. So I'm going to build here an equivalent circuit that emulates the operation of the fuse. So we have the fuse, we have a wire, we have a glass here. This is one example, of course. There are many types of fuses. And what is important here is first of all, the resistance of the wire, okay, in ohms, the electrical resistance, and then the heat capacity of the wire, the thermal resistance between the wire and the walls here, the glass walls, if it's glass, and then the thermal resistance of the glass itself. So these are the units that I'm going to use, and here is an equivalent circuit. What we see here is a classical equivalent circuit of a thermal network. What we see here is the power coming in, which is emulated by a current source. This is I square Re. Re is the resistance of the wire. This would be this voltage here with the temperature of the wire. Then we have the heat capacity of the wire itself, thermal resistance to the glass, thermal capacity of the glass, and thermal resistance across the glass to the ambient. Okay? It is important to realize that the wire itself is a function of temperature. That is, most wires used in fuses have a positive temperature coefficient. That is, as the temperature goes up, the resistance goes up, I'm not going to deal with it. This is just a simplified equivalent circuit, assuming a constant resistance here to the wire. We can simplify this equivalent circuit by actually dropping the last unit here, because the heat capacitance of the glass is very large, much larger than the wire, of course, and also the thermal resistance is much larger. So during the operation of the fuse, which would be for a short time, we can consider this like to be of a constant voltage. So this would be like a voltage source of the wall of the glass itself. In fact, we are more interested in the temperature rise. So this is why I'm going to drop this altogether and just deal with the question of what is the temperature rise of the wire with respect to the glass. So since this is the first order system, we can of course describe it by this exponential equation, and the time constant of course is the product of the capacitor and the resistance. This is time constant. Now we can distinguish here between two regions of operation. One is when the time is very large as compared to the time constant. This is when the temperature almost stabilizes. In this case, this term will be approaching zero, so we are left with this term. So this will be the temperature after a very, very long time. On the other hand, when the time is shorter than the time constant, we can look at the derivative, that is the rate of rise, which is approximately a straight line. And what we find is that the temperature rise is a function of I squared, the time, delta t, the elapsed time, and a constant, which turns out to be Re over Cw. So you see that we already here have this I squared t term. This is the I squared t times some constant. So the operation of the fuse at short times, which is of interest of course, is actually controlled by I squared t. So just to get a feeling of this behavior, I've set up an LT-SPICE simulation circuit. Here we have the current source, which is the power. I'm assuming 100 milliohm resistance to the fuse. Here is the current, assuming 0.2 farad for the equivalent capacitance. This is approximately 200 milligrams of same metal, which is kind of reasonable. And also I'm assuming here a thermal resistance of 500 degrees per watt. I have tried actually to match these values to some data sheet that I'm going to show. They are by no means actually representing a specific fuse, just the behavior of the fuse, although these numbers may not be correct, but this is just for the sake of illustration for educational purposes. So here is the result. What we see here is the time, the running time. We see here the temperature. This is the actually temperature rise, and this is for different currents. Now I've set here a boundary of 1000 degrees centigrade. This will be like if the wire would be of copper. Okay, copper melts at 1000, also silver, but there are many other alloys that are being used. So this is again just an example. Don't take it as a specific equivalent circuit to a specific fuse, okay? So what we see here is that, for example, if the current is 4 amp, it'll take a long time, if ever it will meet actually the 1000. On the other hand, 6 amp is hitting it here, so it'll melt or break it after 80 seconds of 6 amp. However, if the current is 10 amp, then it'll take only like 25 seconds. And then if the currents are much higher, and here there are much higher current, and I have it here zoomed, okay, so these are very high current. We see that 200 amp, we are talking about 50 milliseconds to melt, and 500 amp, it's already below 10 milliseconds, and this is even lower, of course, the 700 amp. We see here actually the two ranges of operation. This is the I2t range in which the lines are straight, while this one is actually the range of the thermal resistance already above this linear range, which is controlled by I2t. So here it's something different. So let's have a look now at the real data sheets and what are they telling us about all these issues. So just an example, I've just chosen this fuse from Little Fuse, this family of fuses, and here are the plots that the manufacturer is actually giving us. So these are different fuses for different specified currents. The one on the right is a 6.3 amp fuse, okay? And I'm going to talk about it, this one here, okay? So you can see that there are two regions here. This region here, which is the thermal resistance one, and here the I2t one. Here you see that the lines are almost straight, meaning that if we are looking at the 6.3 amp, around this current, okay, it'll take a long time. If you are below that, it'll take a very long time for the fuse to blow up. This is seconds, okay, that's 1,000 seconds, okay, that's 10,000 seconds. Only here we can see some action, okay? So for example, at this point, 15 amp, okay, this is 15 amp, it'll blow the fuse after 10 seconds. On the other hand, 200 amp will be 10 milliseconds. And this is very similar to what I've seen in the simulation. You see here that at 200 amp, this simulation shows 50 milliseconds, and 15 amp, it's 10 seconds. While here, 200 amp is 10 rather than 50, and here it's very close. So again, this equivalent circuit does not describe exactly this particular fuse, but the behavior is really the same. Now the manufacturer also gives us this table, which has a lot of information in it relevant to what we were talking about, okay? So let's have a look at this 6.3 amp fuse, okay? So you see that there is information about the cold resistance. It's about 10 milliohm, but as I've already pointed out, this is when it's cold and the resistance goes up quite a bit with temperature, okay? And then we have a nominal melting I2t, okay? So it's 600 I2 times t. And then it says something about the voltage drop on the unit at the rated current, which is 6.3. And then it also says about the maximum power dissipation at 1.5 of the current, which is 1.6 watts. Again, this is similar to what I've done in simulation, but it's not exactly. Now this concept of I2t, which is a measure of the energy or power coming into the system, is actually used in a combined circuit breaker. I'm showing here an ABB product, but there are many other companies who make similar products. And what we have here is actually two actions in this unit. On the one hand, we have a magnetic tripper. This is like a relay. When the current approaches the set point, it'll trip and open the circuit. So this is like a regular relay. On the other hand, we have here a thermal trip, and that is there is a slab here which is heated up by the current, and now the heating is a function of I2t. So this is a load measure rather than the current measure. And when the I2t reaches a certain point, it'll trip. And here is the description that they have here. This is the magnetic tripping, which will be at the high current. And then we have at the lower current, we have the operation of I2t such that for a given current, the time is sort of accumulated, or the power is accumulated, and then it'll trip. And this particular unit that I'm showing here has actually two adjustments, both for the tripping of the magnetic part and also the shape of this I2t portion. So as you can see, there is an application here of the idea of I2t, which is very powerful by actually allowing a higher current for a short time So it's very beneficial. It's not just limiting the operation at a given current, while in fact you can sometimes, like even in an electric car for example, you can actually go to higher current for a shorter time, okay? And this I2t is actually a measure of the energy which the system is dissipating, and therefore the temperature rise of the system. So what are the conclusions here? As I've shown, the I2t plays an important role in the operation of electrical fuses, of course, and then also it's an indication of load rather than current, okay? The power off that goes into the system rather than just the current. Therefore, it could be used to protect system from overload. Now, possible application of the I2t in power conversion system will be presented in a forthcoming video. I hope it will be soon. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.